And we're just going to come up to the phone booth that you mentioned a moment ago.
Yep.
And now tell us what happens. Does a train that's headed to Tahoe, does it normally have to phone from here for further clearance, or it's just a Sanford Lake train?
But on the minimum, you should stop to OS. You should report on sheet that he's in just like got through Sanford Lake.
We've measured the railroad now, Michel, and so the next step in preparing a timetable, since you've got the track plan and the measurements for your miles, is what?
Well, now we have to make a schematic of this track plan. Challenge is to go from this to this. Okay. Now the benefits of this twofold. One, it gives your dispatcher a picture of your layout in an easy to read and manage form. Okay, so the dispatcher would have this either in physical form on a control machine in the timetable and train order days to a computer today. So that would be the computer, and on the schematic the dispatcher will be able to follow the traffic of the trains. And my layout operates on occupancy control system, which where the dispatcher gives track warrants. So when the train leaves Saratoga, he gets a permission to move on to milepost 19. Then the dispatcher will move the little train number, let's say it's train number 101 or whatever, then to milepost 119. And when the operator goes by the station in Corinth, he's going to call the dispatcher and say, dispatcher, put me on sheet OS, and then the dispatcher knows that he's at milepost 19, and then he can give him further orders to move on further. Okay,
and this, but the schematic itself, if we go back to that, this is actually a linear representation of your railroad.
Yeah, no, it's a linear, so you have to unwind your railroad. The next benefit is when you're building your layout, you have a tendency to want to put switches and turnouts everywhere, and it's very dangerous that you get into a loop-to-loop situation. So by doing a schematic like this and unwinding your railroad, you might find some surplus, I call them turnouts and so on, that would not be necessary for your operation, would just confuse the operators as far as the flow of traffic. So this way you got a neat, clean flow of traffic. You know where all the junctions are, and it determines also the points where you want to establish control by the timetable. Okay, you want to establish the stations, you say, and also the junctions. So for example, you would have timetable time for the station at Corinth, you would have a timetable time for the junction at Thurman, you would have a timetable time for maybe milepost 79, which is the entrance to North Creek, you would have a timetable time for the station at North Creek, then when you go to the junction at North River. So this way, you see, you can select all your timetable towns, points, control points, and so on, where you need to inform the operator that he has to report to the dispatcher, or he has to have a clearance to operate between these points, between, let's say, milepost 1998 and milepost 114.5. And that's where the schematic comes in.
And you transferred the your measurements that you took on the actual track plan, you transferred these to the schematic.
Example, milepost 00 to the point called Adley, it's milepost 19, that's 19 feet. From Adley to the Thurman Junction, it's 62 feet. From Thurman Junction to the entrance to North Creek, it's milepost 79, it's 79 feet. See how easy it becomes to manage the railroad all of a sudden?
We've started with the track plan of the railroad. Michel has created a schematic and has talked about how that's done. We've measured the railroad, and Michel has chosen 1 foot as his unit of measurement, and so we've established mileposts along the full length of the railroad. At this point, we're now ready to proceed with the next step in constructing a timetable. And Michel, you've introduced time into it. Maybe you could describe how you've gone and related time and distance on your road.
We've measured, if you remember, we've measured the distance in feet between milepost 193 and milepost 204. And this chart here wants to introduce the concept of time and distance into the model railroad. In other words, the velocity of what speed is the train going to travel, and the train. So time and distance in the to create the illusion of travel in time. Okay. Hence the need for, when you'll see some, when you introduce these concepts, you introduce as well the concept of fast clocks and the short mile. So first you have to determine your short mile. So here we've done that. We take the 11 feet that we've calculated and or measured, and then in using the scale formula, we bring it down to the distance in mile on the railroad here, which is 1.09 mile, a scale mile, if you want to cover the distance of 11 feet. And that's just an arbitrary number determined by that formula. From that number, you introduce the concept of speed, the miles per hour. So if you want to go at 10 miles per hour, 15 miles per hour, 20, 25, and so on, you have a different factor that is generated. Okay, for example, you'll take 7 minutes in fast time clock on a ratio of 6:1, and I forgot to mention the 6:1. That's again a ratio of 6 times the speed of the actual clock. The fast clock will go at 6 times the speed of the actual clock. So,
Michel, if I could just ask you,
yes.
Why did you choose 6:1?
Okay, 6:1 because at 6:1 ratio you can do a 12-hour shift in 2 hours of actual time. If you picked a ratio, and it's sort of a mid-speed of fast clock, if you want, you know, like it's not very fast, it's not too slow either. But I think the main factor is the 2 hours of actual time, because very basically we operate railroads at night after work, mostly on weeknights, and people, let's say, come to your model railroad to operate, let's say at 7:30, they want to leave the house around 10:30, and they want to start operating at 8 o'clock and finish at 10 o'clock. 10 miles per hour. When the train gets to milepost 193 and to get to the yardmaster control point at 204, at 10 miles per hour it takes them 7 fast minutes. If it was 15 miles per hour, it'd be 4 fast minutes. So what you've done, I've built a table like this that takes all the locations, like starting at Adirondack Junction. We've got all our distances we've calculated, all my choices of control points over here, going north to the house from Adirondack Junction. I've got all my distances, I got all my magical distance numbers, and I've got all the time that it will take to get between these points on the railroad at a 6:1 ratio on a fast clock. They have fast clocks today that you can adjust to different speeds.
I have a question here. In building this chart, what did you use in terms of a computer program to do it? And if you changed a number in the chart, would everything adapt to it, or is it a hydraulic type of thing?
This is Excel spreadsheet.
Yeah.
And the only number that's input is the original, sorry, the pen, the number. This is manually put on the spreadsheet. This is a formula that converts this number to that number, and this is a formula that converts this number to that number. I've got all these formulas. And
so if you changed a particular number in a column, then that whole row would
yeah, if I change this number here, the whole row changes.
Oh,
And if you change the fast clock time,
if I change the 6 ratio, it would all change also.
That's very
So if I
convenient.
change, yes, and if you change scales, by the way,
Yeah.
right? Because here we're in the formula to get to here, I use 87 as the HO scale. But if you're in N scale, you just change that number to 160. So you say 160, and then all zoom, you got all your line. What happens is I use this table output, the output here, to build my next step which we'll get into in pretty soon there, which is building the actual timetable.
Okay, we've now completed the calculation of train speeds and distances, and we had a number of different speeds. Michel showed us a graph, a table that had a variety of train speeds, and I assume, Michel, that you use that because you have a variety of different kinds of trains, and so some trains are obviously faster than others, and you have some steep grades on your railroad. Maybe you could go to the next step now and show us how you use these this speed and time relationship.
Okay, so again, I'm using the Excel spreadsheet. So I do this on a spreadsheet basis because it gets a little area if you start doing this manually. Well, you can do it manually the old way. They used to do templates, and in between each of your stations they would have another factor, which would be the distance of the square would be a different size for each distance. Okay, but that's in the Bruce Chubb book, and it used to be done like this. On a computer you don't have to do this. What you do is you take your time distance chart, your time distance, for example here the elapsed time we said between 193 and 204, for example, it was 7 minutes in the fast clock. So you build a new spreadsheet that lists all the same stations that you had here, all the mileposts and the distances that you had. All you have to do is copy it into the cells, and then you write your distance going northbound, your distance going northbound, your distance going southbound, because when southbound you start at 0 here, and northbound you start 0 down there, and then you pick your speeds. Okay, the speeds here are taken manually from my table here.
And this is chosen based on your concept of the size of train, how steep the grade is, and how fast you want a particular train.
Right here it says speed, miles per hour, or trains. I've got 3 tables like this. One for or trains, one's for general freight trains, and one for passenger. Each one has got various speeds chosen for certain locations. For example, an ore train between North River and going north, between North River Junction and Sanford Lake, and it's maximum 15 miles per hour. Okay, going down southbound, the same thing. Like it starts at 10 miles per hour, goes down maximum 15 miles per hour. Okay, going down, and but a passenger train could be 25 miles per hour. Okay, much lighter. Okay. So in this table here, so what we derive here is, okay, so we've picked up the speed, and the speed gives me the running time, 7 scale minutes. That is converted into a factor that I can use in the timetable itself. I can pick this number, and then to derive, we'll use it in the formula to build the time in the timetable. Okay, from the time between, let's say, the 204 and 193. So now we're ready to start building the worksheet for the timetable itself. And you can see on the format here, the format has changed, and now we're getting ready to build a timetable. We've already got the frame for the timetable, we've got the mileposts lined up, the stations, and we've now picked our train names that from our operations planning that we did before. And from there we're going to now apply the formula required to build the actual time on the timetable. So the first thing you have to do is, for this example, we'll pick one train, the ore train, and we'll take the ore train will be going southward, so leaving Tahouse, going to Adirondack Junction, milepost 00. Okay? So first you have to pick a departure time. So this is your first most important train, as we discussed before. So we're going to pick departure time. The departure time is 1600 hours for this train. Then we have to move this train down. He's going southward, so southward the schedule says read down. And so now we're going to move this train along the timetable to its destination at Adirondack Junction. And to do this, we have to insert a formula to each cell that would build the time distance itself, incorporate the time distance itself into the timetable. So the formula is, in this case, the previous cell, which is the departure time, plus the dollar sign here is to maintain a constant it's a tool used in Excel, plus the cell containing the time factor derived from the time distance table, and this is the number here, southbound 0.012. remember, it's our 7 minutes converted into a time factor, becomes 0.12. You take the 0.12 and you put it in here, and then you multiply, that's the multiplication sign in Excel, by 1, and this is because I already picked all my speed factors myself. If you remember, I said I chose all my speeds, various distances, various speeds, because I've got grades and so on. So I don't have to have a factor here of, let's say, growing my speed constantly by 1.25 or 1.35 or 1.75, you know, which people could do by, you know, you could say I'll use the same speed but I'll grow it for each train by a different factor. In this case, I chose a constant speed factor. Then these numbers I divide by, this is the division sign in Excel, divide by 24, and this converts my factors into hours and minutes. Okay, and the number becomes 1607, 7 minutes. Okay, so now the next cell is the same thing. So you keep applying, you copy you copy this, you apply that the factor, the next factor, 13, and you carry on, and you get to the station at North Creek at 1650. There, you might want to stop for 5 minutes. The guy wants to go get train orders, because remember, the ore train, it's a long haul coming down the grade and so on. So they stop 5 minutes, check with the dispatcher as to their clearance, and make sure that they have a clearance to carry on to Adirondack Junction. So we got a 5-minute pause. There's a table in the spreadsheet that will incorporate a station stop sign of 5 minutes. The formula is slightly different. I could show you the formula there. Okay, so as we were saying, we arrive at North Creek Station at 1645, and we want to do a 5-minute stop. We want to start at 1650 again. So the formula would be derived from picking the time factor, the same way that we did the factor in the time distance table. But here we're going to take, let me find it there, North River, North Creek, switching, northbound, switching, station stop, 5 minutes. The factor is 0.08. Okay, so now you incorporate that in the formula, and the next thing you know, you leave at 1650, and you carry on from 1650, just like you did at 1600. You carry on with your other formula and all the way to Adirondack Junction.
So what you've done here is you've managed to create a situation where you can now apply time to different activities that have to occur on the layout.
Yeah.
So the example you gave was the station stop, but there's other things going on there too.
Yeah,
maybe you can describe some of the different ones that you've used and how you kind of determine the minutes.
Okay. Well, the minutes are pretty much arbitrary. Okay, so I allocate minutes. Okay, so at Sanford Lake, when they drop facing cars and siding, give them 60 minutes to do that, and when they pick up cars, another 60 minutes. So they've got basically 2 hours to do the job there. Okay, and then it gets down to, it gives them a factor of 1 hour, you know.
Yes.
And the factor of 1 hour gets incorporated in there, and you can. I'll show you a place there where it actually happens. So let's take Sanford Lake. Let's take where they would, you see the train terminates there, so I don't have to worry about that one.
Yeah.
That's I had that formula because I did some different scheming, but let's see here, arrives at, he has to drop cars at North Creek, okay? The train leaves at 14:15, that's the freight, the regular freight.
Yeah.
He always has some empties to drop at North Creek, so he gets at North Creek at 14:32,
Right.
okay, and leaves at 15:32. So there's, the formula is applied here, okay?
Yes.
The 1 hour. So he's got 1 hour to drop that car. And by incorporating the factor into timetable, the magic is when you change this time, let's say you want to change that to 15:15, for example, the whole thing changes automatically, you know. So you, and then we'll see what happens to the string diagram after. Okay, you can link this to the string diagram. That's the secret of the. So
the value of the worksheet is it allows you to combine your time distance of trains traveling over the line plus the time it takes to actually do the activities.
Time. Yes, activities time, the combination of the velocity, like Doug says, and as well the time to actually do the work, incorporate it in the thing. Okay, so from the worksheet southward only, so from this worksheet and the development of this formula, we've now got this column defined, and now we're going to move on to building the old timetable.
That column specifically for the ore train.
That column specifically for the ore train. So that's our first train we put on the timetable.
Yeah. And you built other ones as well for each train that you have,
Yes.
right?
So yes, all the other ones have been built with the same fashion, and they've been incorporated one by one, you know, because as we incorporate these trains, we have to make sure that these trains can meet other trains, can have room at the end of at Adirondack Junction to move into staging. We have to make sure that the operators are available to run these trains. So each train has to be incorporated in the timetable one by one in a string diagram built as we go that will tell us where they will meet, which other trains will interfere or flow with them. So now it's time to get the music going, as they say, you know, and make sure that the orchestra is going to all function with the dispatcher managing the whole thing.
So this is really just half of what a timetable would look like.
Exactly. So let's pick our 1607 number here, and let's go see on the whole timetable worksheet with all the trains incorporated, okay, including all the potential extras, you know. Now I've incorporated the potential extras, but here's our train, 1607, and here's the train when it leaves in the morning. It's like the first section of 303, 6:30 in the morning, leaves at 6:30, gets to Tahouse at 8:02, and so those are the two that I plug in first, and then I go, I use the tool in Excel to build the string diagram, okay? And the chart is easy to do. You just follow the Excel and formula, and it gives it to you automatically. You select your numbers, you select your column, and your column will give you a string, and then you go and look at the string. Anyway, so.
Okay. Before we go and look at the string diagram, just an observation or two. Michel has shown us the general case here, where the train speeds can be different, where we've used a fast clock, where there's the mileage has been represented on the railroad by measurement. There are ways to simplify this. For example, a wall clock could be used, and then there wouldn't be the scale factors introduced for time. Another way to simplify it would be to say that all trains run at the same speed everywhere, and then we wouldn't need different times between stations, and we would need different times for passenger trains and freight trains. But all of this is just a simplification. The general case is the way things would run on most railroads, and that's what Michel has done on his.